Hello everyone. Last time, one of your classmates asked me about the use of second derivative test. What happens if the second derivative test fails? To begin with, I'd like to give you a summary of second derivative test. So first of all, if you are given a differentiable function f of x, okay? And the first thing is to identify all the stationary or critical points. As I mentioned in class, different authors will have different definitions for stationary or critical points. But in this unit, we simply use the following definition. A point is critical or stationary if its derivative equals 0 or its derivative does not exist, okay? So when you are trying to apply the second derivative, you have to check the derivative to check the derivative that is equal to 0. So for instance, you are given a differentiable function f of x, and then you are trying to find whether or not this derivative equals 0. And find all the points that satisfy this equation. And then its second derivative is greater than 0. It means that the graph is concave upward. So you have a local minimum. Okay? By contrast, if the second derivative is less than 0, then you have local maximum. All right? However, if the second derivative equals 0, then this is inconclusive. This means that you do not have any conclusion whether it is a local minimum or it is a local maximum. And in other cases, there is no local minimum or maximum. Okay? So today we will talk about how to address this situation when you arrive at an inconclusive situation. So my suggestion is that we can go back to use the first derivative test. So if inconclusive, then probably it is the best practice to apply the first derivative test. So for the first derivative test, if you notice that f prime of x is greater than 0 for x that is less than c, and m prime of x that is less than 0 for x that is greater than c, it simply means that your function increases and then decreases, okay, f of x. So in other words, you have a local maximum at c, right? For the other case, if f prime of x that is less than 0 when x is less than c, and f prime of x that is greater than 0 for x greater than c, then in that case we have decrease and then increase, okay? This was your f of x and x equals c. So you have a local minimum. And here, for this case, I have local maximum, okay? So this is how we can apply first derivative test for inconclusive situations you might reach when applying the second derivative test. Okay, I think it is always a good idea to go through some examples. So let's take a look at two examples. The first example, f of x equals x cubed. Okay, so now let's check the stationary points or critical points. So we have f prime of x equals 3 times x squared. Okay, and for here we have found that critical point which is x equals 0. All right. And then let's check the second derivative, f double prime of x, which is equal to 6 times x. And the second derivative at the critical point, 0, equals 0. So we have arrived at the inconclusive situation, right? Okay, so how about f prime of c when c is greater than 0? So you substitute a positive c here, you have 3 times c squared, which is greater than 0. Okay? C is greater than 0. And also, f prime of c is greater than 0 for c is less than 0, right? Because we have c squared. So no matter c is positive or negative, f prime of c is always positive. Okay? So maybe I can use a more compact notation to denote this idea. So f prime of c equals 3 times c squared, which is greater than 0 if c does not equal 0. Okay? So as you can see, in this case, we have the increase at x equals c, and then increase again. So this means that at point 0, this point is neither local minimum nor local maximum. Okay? And if you like, you can draw this figure using any graphical illustration tool. And you notice that this function looks like this one. All right? So here, this is x0 equals 0. And the derivative equals 0. However, it is neither a local maximum nor a local minimum. Okay? So by applying the first derivative, we understand that the point 0 is neither local maximum nor local minimum. This information cannot be obtained using the second derivative test. Okay. All right, so let's talk about the other example I'd like to show you, which is f of x equals x to the power 4. Again, this function is differentiable, right? So let's take the first derivative, f prime of x equals 4 times x cubed. And the critical point, which is 0, right? Because when you substitute x equals 0 into the above equation, you get a 0 value. So x equals 0 will be your stationary point. And then f double prime of x will be equal to 12 times x to the power 2, x squared. And unfortunately, we have f double prime at 0 equals 0. So we have inconclusive situation when you are applying the second derivative test. Okay, so let's try to apply the first derivative test. So first of all, if x is less than 0, then we have, I'll use another notation. Let's use c. If c is less than 0, then f prime of c is equal to 4 times c cubed. Now c is a negative value. As a result, this one is less than 0, right? If c is greater than 0, then f prime of c equals 4 times c cubed, which is greater than 0. In other words, if this vertical line represents x equal to c, x equals 0, then when c is less than 0, the function is decreasing. When x is greater than 0 or c is greater than 0, the function is decreasing. And in other words, here x equals 0 gives you a local minimum. Okay, So as you can see, by applying the first derivative test, we conclude that x equals 0. This stationary point gives you a local minimum. And this statement cannot be obtained using the second derivative test. And again, you can use any graphical illustration tool to draw the graph of this function. It actually looks very similar to the y equals x squared, right? So I'll show you this one. So this function is y equals x to the power 4. Okay, so this is a concave upward, and it has the slope of 0 at the origin. But definitely this point is the local minimum. Okay, so these two examples are very interesting. These two examples cannot be solved using the second derivative test to give you the information about local extremums. However, you can still apply the first derivative test to understand the behavior at least 2 critical points. So my advice is that, if possible, use the first derivative first. Okay, usually first derivative can give you sufficient information about local extremums. All right, so this is the procedure for addressing the inconclusive situation. Thanks for watching this video.